Hello everyone. As we were discussing heat equation in one dimension, so continuing the same topic, today we are going to solve the questions related to it. And today's question is, an insulated rod of length L has its ends A and B maintained at 0 degrees Celsius and 100 degrees Celsius respectively until steady state conditions prevails. Now, if B, the other end, B is suddenly reduced to 0 degrees Celsius and maintained at 0 degrees Celsius. Now, just keep one thing in mind, we have not changed the temperature of end A. Now, what we have to do, we have to find the temperature at the distance x from A at time t. So, what is the situation right now with us? We have a rod of length L, and this is our end A, this is our end B. So starting what we have done, we have maintained the temperature at end A as U is equal to 0 degrees Celsius, and at B we have maintained at 100 degrees Celsius. Later on, after the steady state conditions prevails, what we have done, we have taken the temperature of B to lower side and reduced it to 0 degree Celsius. We have not changed the temperature at A at this position. Okay, so we have to find the temperature distribution. Since we know that it is a statement of heat flow, so that means one dimensional heat equation will be applicable. So the solution of this statement will be the given statement problem relates to one dimensional heat, or you can say diffusion equation, heat equation, that is curly to u by curly x square is equal to 1 by c square curly u by curly t. Let it be equation number 1. The possible and compatible, both solution of 1 is u of xt is equal to c1 cos of px plus c2 sine of px into c3 e raised to power minus of c square p square and t. That will be equation number 2. Now, how we obtain this one, I have explained that concept in my previous video. Okay. Now, further what we have been provided. Now, since we know that there is a rate of flow of heat, okay, so these are the two initial conditions, and here is the boundary condition. So that means our total solution will consist of two parts. That is, first one will be the steady state and the second one will be the transient state. Okay, so the given solution u of xt, or you can say the required solution, okay, u of xt will consist of two parts. Number one, that is steady state, which is mentioned as us of x. It doesn't depend upon the t. Okay. Number two, that is transient state, that is ut of xt. Okay, it depends upon the time. So starting with the steady state conditions, so for initial temperature distribution, that is known as transient state. So what we have, u of t, that will be equal to initial temperature at A, that is 0, plus final temperature at B, that is 100, minus temperature at A over length of the rod, that is L, into x, the variation x. Okay, so it comes out to be 100x by L, that is a ut. Now for final for final temperature distribution, that is steady state. So here what we are having, US, that is equal to temperature at A plus temperature at B minus temperature at A over the length into X, and that is equal to what? That is 0. Okay, so that means therefore the total temperature U of xt will be the sum of US of X plus UT of xt. Now US of X we have calculated, that is 0, and UT of xt, that is what? That is this temperature, this value, number 2. This will take as a final distribution value. Okay, so that will be C1 cos of px plus C2 sine of px into C3 e raised to power minus of c square p square and t, and that is equal to U of xt. I hope till this step is it clear. Now let be equation number 3rd. Well, I'll take this one as 3rd and this one as 4th. Okay, now when we are at end A, okay, so that means at x is equal to 0, the temperature function U was 0, so equation number 4 will reduce to 0 is equal to C1 cos 0 1 C2, this sine 0 will be 0 into C3 e raised to power minus of c square p square and t. Since we are working on the position of x, so t is independent right now, so 0 is equal to C1. So we get the first constant C1 as 0. Substituting equation number 4, so equation 4 reduces to, that is U of xt will be equal to C2 sine of px into C3 e raised to power minus of c square p square and t. So I'll take C2 C3 as Bn, C2 C3 into sine of px into e raised to power minus of c square p square t, that is U of xt. Okay, now what is the next boundary condition? That will be equation number 5. Now the other end at x is equal to L, that is the end B, and again here the function U was what? The final function of U will be equal to 0. Okay, so equation 5 reduces to 0 is equal to C2 C3 sine of PL into e raised to power minus of c square p square and t. From this part either C2 C3 will be 0 or sine of PL will be 0. Now if C2 C3 will be 0, if I substitute over here, the whole temperature distribution function reduces to 0. So that means this is not possible. So we have only the one possible solution, that is sine of PL equal to 0. That means PL is equal to n pi, or we can say P is equal to n pi by L. Now we will substitute this value of P in equation number 5. So equation 5 reduces to U of xt is equal to C2 C3 into sine of Px, that is n pi x by L into e raised to power minus of c square p square, that is n square pi square over L square into t, and that is our equation number 6. I think so till this step it is clear to everyone. Now we have to find the value of C2 C3. Basically it is Bn. I'll mention it over here, that is summation Bn into sine of n pi x by L e raised to power minus of c square n square pi square over L square into t. This will be equation number 6. Okay. Now we have one more condition which we have obtained, that is transient state condition. So using or applying transient state condition, that is at time t equal to 0, we know that U was 100 x by L. We have calculated this value. Okay, So substituting in equation number 6, so equation 6 will be 100x by L is equal to summation of Bn into sine of n pi x by L into e raised to power minus of 0, something power 0, that will be 1. So what we received over here, so we get 100x by L into summation of Bn into sine of n pi x by L. Now using Fourier series, so we can find the value of Bn will be 2 by length of the rod, 0 to length of the rod into this value, that is a function 100x by L into this value, that is sine of n pi x by L into dx. Now we have to use u into v formula to find the integration of this one. So first of all, 2 by L into 100 by L, that is a constant, so I will take it common, 0 to L. So we have x into sine of n pi x by L into d of x. We know that the integration of u into v, that is a single step solution, is u as it is, v integration minus u derivative, v double integration plus u double derivative, v third integration minus u third derivative and v fourth integration plus so on. Basically it is an alternating series, positive, negative, positive, negative, positive, negative. Initially we don't need to take the derivative of u, we start with the integration of v, then in every step we take the next derivative. For this one, here we have u, here we take u first derivative, u second derivative, u third derivative, u fourth derivative and so on. And similarly from this one we will take first integration, v second integration, v third integration, v fourth integration and so on. Let us apply this concept. So here the value of Bn will be 200 by L square. Now this is our u and this is our v. So u as it is. Now integration of sine, that will be minus cos of n pi x by L over coefficient of x, that is n pi by L, minus, now u derivative, x derivative will be 1, then double integral of v, so we again take the direct integration of this part, so minus will be as it is, cos integration will be sine of n pi x by L over n square pi square over L square. Why I have taken n square pi square over L square? Because we need to take coefficient of x, that is n pi by L, and 1 n pi by L we have already from the previous step. Okay, plus now derivative of 1 will be 0 because we have to take double derivative of u, so that will be 0, so no need to take further question. So it will be 0 to L. Now, so 200 over L square into minus L over n pi into x cos of n pi x by L minus and minus plus L square over n square pi square into sine of n pi x by L from 0 to L. So it will be 200 over L square. Now upper limit minus lower limit, L over n pi, L into cos of L and L cancel out, so we get n pi plus L square over n square pi square, L and L cancel out again, sine of n pi minus, this was the upper limit, minus lower limit 0. So minus, this is 0, 0 into something 0 plus L square over n square pi square, sine 0 is 0. So this step is completed, this one. Now we have 200 over L square into minus of L into L, L square over n pi, cos n pi is minus 1 raised to power n, sin n pi is 0, so no need to write that again. So we get 200 over L square into minus of L square over n pi into minus 1 raised to power n. So L square and L square cancelled out, so we get minus 200 over minus 1 raised to power n over n pi. This is what? This is the value of Bn. Now where I need to substitute this value of Bn? We need to substitute this value of Bn in our equation number 6. Okay. So substituting value of Bn in equation 6. So we get u of xt is equal to summation n from 1 to infinity minus 200 into minus 1 raised to power n over n pi into sine of n pi x by l into e raised to power minus of c square p square t. P square, we need to substitute the value of p square also. C square n square pi square t over l square. Okay, since minus 200 over pi, that is constant, so I can take it common. Minus 200 over pi common. So we have summation n is from 1 to infinity. We have to keep all those terms which consist of n inside this bracket. Sin n pi x by l into e raised to power minus c square n square pi square t over l square. So this is our final temperature distribution function, which is the required temperature distribution function. Hope it is clear, and rest questions I'll solve in next videos one by one. Okay, take care, goodbye.